Manny Landron here. Manny's a principal information security consultant with Align Technology Group. Extensive experience building, securing, and monitoring high-value and well-regulated applications and platforms on premises and in the cloud. He's led teams that implemented the Greenfield Information Security programs for AAT Insurance, which is a specialty insurance group with about $2 billion in underwritten premiums, and also for Citrix ShareFile, which is a Gartner Magic Quadrant leading content collaboration solution hosted with AWS and Azure. Manny is a graduate of Virginia Tech, another Virginia Tech tie this morning, and a veteran of the U.S. Army. He enjoys spending time with his family and playing his violin and also hiking in Umstead. So with that, I'm going to turn it over to Manny and let's get started.
Thank you, Chuck. Appreciate it. So thank you, BSides, for the opportunity to present today. And thanks to all of you for attending. So I'm Manny Landron, and I help organizations secure and monitor their information technology platforms and applications on premises and in cloud. Today, we'll be covering a talk called Understanding and Securing Containerized Environments. As far as agenda is concerned, it's right here. So we'll provide you with an overview of container security with an emphasis on the fundamentals and differences between containerized environments and virtualization, the pros and cons of containerization from a security perspective, and the challenges associated with securing and monitoring containers throughout their life cycle, from container registry on through production. We're also going to explore the concepts of container escape, review the role of kernel namespaces and control groups, and the role they play to enforce segmentation and control resource allocation. And then we're going to gain an understanding of container runtime behavior and the importance of implementing safeguards, including least privilege access to promote container isolation. So a container image, differs somewhat from an actual container. You build a container from a text-based script of instructions, usually a Docker file. An image executes code in a container. So think of a container as running an instance of an image. A runtime environment is the environment in which the program or application is executed. It loads the application and runs it with all the resources necessary for the program to run independently of the operating system. And then simplistically, it's software that's designed to run where before it actually installs. So containers and virtual machines have similar resource isolation and allocation benefits, but function a little bit differently because a container virtualizes the operating system instead of the hardware. Containers are also much more portable and efficient than virtual machines because containers are typically much smaller in size and therefore take up less space. Containers are an abstraction really of the app layer that packages code and dependencies together. So multiple containers can run on the same machine and share the operating system kernel with other containers. And then each is isolated, an isolated process rather than user space. So virtual machines or VMs are an abstraction of the physical layer. And you have one server running you have many servers rather virtualized running on one server, one server. The hypervisor allows multiple VMs to run on a single machine, and each VM includes a full copy of the operating system along with the application and any necessary binaries and libraries as well. VMs are typically much larger than containers, and traditional VMs can be really slow to boot. There are new VMs like Amazon's Firecracker and Kata that are lightweight VMs that do start in milliseconds rather than minutes, but typically they take a lot longer to boot. I'd like to highlight a couple of terms in the event. We have some folks in the audience that are not familiar with them. So user space refers to the code in an operating system that lives outside the kernel. The operating system kernel is the central module of an operating system that's really responsible for managing all the resources, so memory, processes, devices, the disk itself, system calls, and more. And the fundamental difference between containers and virtual machines is that virtual machines run an entire copy of the operating system, including the kernel, while containers share the host's kernel. As a result, container isolation is technically weaker than that provided by a hypervisor in a virtual machine use case. So engineers create managed containers to run applications, relying on a combination of continuous integration, continuous delivery, or continuous deployment pipelines. Popular containerization solutions such as Kubernetes, Docker Swarm, Amazon Elastic Cloud Container Service, rather, ECS, to name a few. So Amazon Elastic Container Service is fully managed. It's a fully managed container orchestration service. So Amazon Elastic Kubernetes Service, or EKS for short, is a managed service that makes it easy for you to run Kubernetes on AWS without installing an operating system, owning your own Kubernetes control plane, or worker nodes. Worker nodes basically is a machine that hosts one or more containers. And then you can build and deploy container images using traditional virtual machines, as well as serverless computing engines such as AWS Fargate. So AWS Fargate is a serverless compute engine for containers that works with both Amazon ECS and Amazon EKS. Each Fargate task has its own isolation boundary and does not share the underlying kernel, CPU, resources, memory resources, or network interface with another disk. So I credit Liz Rice, the author of Securing Containers, for this image and list. This slide represents she wrote that book. It's published by O'Reilly. If you haven't read it, if you don't have a copy of that, please get it. It's well worth the read. She's very succinct with her writing. I think the book in its entirety is about 160 pages and covers a lot of great detail. This slide represents a high-level overview of the common risk associated with containerized workloads. So, software vulnerabilities in the host operating system and third-party apps, as well as all the misconfigurations in the host operating system and container, they introduce exploitable vulnerabilities that may lead to privilege escalation and container escape. It's also important to consider the security and trustworthiness of the build environment and the container registry. You want to ensure that the integrity and trustworthiness of the container images used to instantiate the container applications in production, and to avoid introducing untrusted and unauthorized images. So managing secrets also remains a challenge, but orchestration platforms like Kubernetes and Docker Swarm, along with secret vaults like HashiCorp Vault and AWS KMS, they've introduced the capability to more securely manage secrets throughout their lifecycle as well. So credit Julie Evans. She's at Bork on Twitter. She publishes zines on wizardzines.com. Her zine, How Containers Work, goes for about $12 and is entertaining introduction to how containers work. Recall that applications are not run in user space and need to communicate with the kernel, right? The Linux kernel, using system calls to do things like read and write data to a file, open or change the owner of the file, execute another program, create or kill a process. And remember that a Docker container, or a container period, is a process. There are hundreds of possible system calls depending on the version of the Linux kernel that's running. And applications don't really need all the system calls at their disposal. Therefore, evaluate the profile of the system calls and the application that the application makes throughout its lifecycle to determine whether the appropriate system calls are present and they adhere to the principle of least privilege. So next, we'll use strace, or at least I'll show you how I used strace, a Linux debugging utility that monitors interactions between processes and the Linux kernel itself, which includes system calls to observe what occurred when a container is terminated. So a little setup is required to use strace. And again, strace is primarily a debugging tool. It's very capable. This isn't intended as I'm not proposing that strace be the primary tool that you use. There are several third-party solutions, commercial off-the-shelf or open source, that provide similar capability. This is just a readily available tool, in the Linux toolbox that you can use to evaluate what sort of system calls are made, whether for educational or academic purposes, or to evaluate whether a container is making proper system calls to the kernel. So again, a little setup is required to use strace. You run sudo docker ps to list all the containers running on the host. Note that the process ID isn't listed by default when you run docker ps. So to obtain the process ID, take note of the container ID and run the docker inspect command you see on the screen to look up the process ID. And you'll get copies of this slide, I'm sure, of these slides, I'm sure, so you don't have to take a picture or write it down. Next, run sudo trace with the P switch for process with the associated process ID, which in this case is 4691. In another terminal, I terminated the running container, and strace captured the raw output, listing all the system calls made to the kernel. It's cut off, but in a second I'll show you the summary of those system calls. Let's see what else is important here. So again, strace is just it's really a debugging tool that you can use to at least evaluate what sort of system calls a container is making, or any process for that, whether it be PWD for your present working directory, LS, it doesn't matter. If you're interested in doing that, it's really easy to do. Just make sure that it's installed, and then you can go ahead and start using strace at your liking. So here we use strace to view system calls and put it in a table format using the C switch. Note that the process ID changed because I instantiated a new version of the containerized application. This application wasn't doing much. It was a Pixie vulnerable API. As much as I tried to interact with it, I couldn't get it to actually make a system call until I actually terminated the container itself. So we used strace to provide you with an idea of what occurs under the covers, but bear in mind that strace, while capable, does have its limitations. However, there are open source solutions, again, like Tracy. Tracy is one that you can use in place of strace that serve a similar purpose. And then open source and commercial solutions that rely on their capability to observe and filter calls to monitor and secure the host and containerized applications. These are typically bundled with cloud-native application protection platforms. Some that come to mind are Aqua, Sysdig, Trend Micro's, Cloud One, that sort of thing. So while I'm not prepared to give you a primer on Linux permissions today, please note that Linux, or at least in Linux, everything's a file. And file permissions do dictate who or what can access that file and what actions they can perform on those files. Understand that containerized applications run as a process, and most run as root, albeit with limited capabilities. Consider that there are rootless alternatives, right, that you can use to host containers that are emerging that promise to eliminate the need to run a container as root. So be sure to review the containerized workload to determine if it's running as root and if it's an absolute requirement for it to run as root. Otherwise, take steps to effectively limit permissions as necessary. You can also run sandboxes on the host to filter those system calls as well. And then you can review those capabilities, and we'll show you how to do that in a second to determine whether those capabilities are necessary. Note that the setUID flag can be pretty dangerous because it might give an unauthorized user root access, or at least access to run a program under another user. Consider that the setUID sets the effective user ID of the calling process, and a container is typically running as root. So Linux divides the privileges traditionally associated with superuser into distinct units known as capabilities. Would be independently enabled and disabled. The capabilities can be independently granted to processes, including container processes. You can use the getCaps command along with the process ID of the container to identify the list of capabilities that are enabled. You can reference the capabilities man page to learn more about each capability. Provides a definition of what the capability, what sort of privileges that capability grants. While this container doesn't have the capsys admin capability enabled, I highlight it here because it should be avoided, as it enables many of the privileged capabilities associated with root. You'll see later when we talk about containerscape briefly that the capsys capability is typically what is leveraged through a vulnerability in a kernel to one, escalate privileges, and then two, escape the container itself. You also want to avoid running containers and in privilege mode or root mode with the -- privilege flag. Although a container may run as root by default, again, several of the capabilities are not granted by default. Privilege mode means that if you are root in the container, then you essentially have full privileges of root on the host system itself. Recall that containers run as a process, right? They are a process. Even though they have an application running, even though they have dependencies and libraries, they do run as a process. There are 3 essential Linux kernel mechanisms to limit a process's access to host resources: control groups, namespaces, and then changing the root. So control groups are a feature of Linux that limits accounts for isolation. It isolates resources, including CPU, memory, disk I/O, and network, and any process that any process can consume. Namespaces are a feature of Linux, and it partitions kernel resources such that one of the set of processes doesn't see other resources that other processes have access to. You can also view the namespaces available on your host operating system by using the ls-ns command there. And I highlighted, for example, the process ID namespace. There are several namespaces. And one example is the PID namespace, which provides processes with an independent set of process IDs, including process IDs that spawn from the parent process IDs, those child process IDs. Another example is space. This one's important because it provides a mechanism to map the root user inside a container to a limited privilege user on the host itself. You can see the host, or rather, you cannot see the host entire root, or rather the file system from a container, typically, because the root directory is changed during container creation. This effectively limits the set of files and directories that a container can view. So this particular vulnerability, CVE 2022-0185, was identified in January of 22. And recall that capsys is largely a catch-all capability. It can easily lead to additional capabilities or full root, typically granting access to all capabilities. So this container escape vulnerability materialized because of an issue in a Linux kernel, but container escape can also result from issues with misconfiguration as well. It doesn't have to be a vulnerability in the kernel or in the operating system. Typical mitigation steps include, obviously patching the kernel, applying the necessary patch, but compensating controls can include minimizing the use of capsys the capsys capability, using a sandbox like seccomp to effectively filter system calls. The default seccomp profile is usually enough, and more recent Docker implementations actually implement seccomp by default. So here we start talking about each of the security considerations for a containerized environment. I listed them out so that when we do share the slides, they're readable, they're digestible. So you do want to scan images in the registry for vulnerabilities, right? So registries, especially public registries, can be untrusted. So do take great care in evaluating the images that you use. The best approach in certain cases, especially when you're considering hosting sensitive workloads, is to create those images yourself. Apply available updates to third-party libraries, including applications, before you introduce it to the build, or at build rather. So before you introduce it at production, you don't want to do that at runtime. Cryptographically sign the images to ensure its integrity and trustworthiness. Once you create an image, it's important that you take steps to validate and preserve its integrity. And also admission control safeguards that are largely part of orchestration solutions like Docker and Kubernetes, Docker Swarm and Kubernetes rather. They depend on that. They can depend on that signature to evaluate the trustworthy image before they actually introduce it to the build cycle in production. So keep registries private if it doesn't need, right? And do take great care when you evaluate and select images that are in public repositories, as they can contain malware, they can contain vulnerable third-party libraries, dependencies. And of course, you need to do code reviews to evaluate what the code is actually doing. Secure the build process, again, to protect the image of the integrity of the image, but only allow approved images to deploy in production. So then you want to secure the host, just as you have been doing for years, right? This is really the one constant. Build a host from scratch if you need to, right? There are certain workloads, sensitive workloads, that you should rely on a built from scratch host, or use a trusted baseline. The Center for Internet Security benchmarks do a great job. However, they don't produce benchmarks for every single operating system version. Configure the host operating system according to CIS benchmarks, but again, if it's available, right? Use a minimal operating system, purpose-built to host containers such as Alpine or CoreOS. These operating systems typically remove unnecessary libraries, dependencies, functionality, and you reduce the attack surface. And of course, they're much more lightweight as well. Consider using a minimal operating system. Scan the host operating system for patch and configuration-related vulnerabilities, obviously before you introduce it to production. And then, of course, in production, consider refreshing the host operating system as opposed to patching it. If you can work with your engineering team to figure out a way to automate and take advantage of, immutability, ephemerality. Immutability meaning that if you agree, for example, to enforce immutability in a production environment, that means that anything in production doesn't really change. You're not patching, you're not adding any third-party software, you're not making any configuration changes. The preference would be to introduce an entirely new operating system host, right? An entirely new container that has been patched in the application delivery process to ensure that it's easier to manage and to ensure that you don't have a lot of configuration drift. Apply available updates to the host operating system as usual, and then leverage a sandbox or Linux security module to enhance isolation. These come in the form of SecComp, AppArmor, SE Linux, gvisor, though gvisor is really a hybrid between a virtual machine and a Linux security module, or a sandbox rather. And list it. There are ways now to host containers in very lightweight, very fast virtual machines. Again, Kata comes to mind, AWS Firecracker comes to mind. These are really lightweight virtual machines that operate just like typical virtual machines, but they load much faster in milliseconds rather than minutes, and they're much smaller. So if you have a sensitive workload that you need to ensure the isolation for, and look, virtual machine isolation is, for the most part, tried and true, it's proven. And it does add another layer of defense for very sensitive workloads, as opposed to relying only on the kernel within the operating system itself. You can argue that the kernel has been around for a while too. However, the kernel occasionally does reflect or materialize some vulnerabilities as well. Secure the container. Run containers as non-root users if possible, or a pared down version of root, right? Remember the capabilities we talked about? Not all containers need every single capability. And they don't need every single namespace either, right? So avoid running containers in the privilege mode, as we talked about, because essentially that overrides all security checks. You are true root in the container when you're running this privilege mode, right? So you override any sandboxing, any Linux security modules, those kinds of checks. You basically get a pass. Remove unnecessary Linux capabilities, as I just discussed, and then leverage a runtime protection solution to ensure that only authorized executables run. These come in various forms. It could be a traditional anti-malware solution, or it can be a anti-malware solution that also incorporates some degree of syscall filtering. Perform continuous cloud security posture management, leveraging open source or commercial off-the-shelf solutions. These cloud security posture management solutions not only evaluate how well your environment, typically your cloud platform, is configured, but also the services within that cloud platform as well. Run containers on hosts dedicated to running containers, right? Don't mix and match workloads on a operating system host. Avoid mixing sensitive and non-sensitive workloads on the same host, because there's always the possibility of container escape. The isolation boundary with the kernel is not as strong as it is with a hypervisor and in a traditional virtual machine use case. And then also, while not listed here, do consider hosting workloads or containers rather that communicate parties or external third parties outside of the network with those that are only communicating internally. So very much like we segment our existing on-prem networks, you should also segment your containerized environment. Then add executables to the container at image build time, not runtime. I alluded to this earlier, because you do want to ensure that the integrity of your containerized application. And then you also want to avoid drift, configuration drift, right? You end up with an environment that's using different versions of a library, different versions of a dependency. And ultimately, it's really hard to secure an environment like that. It's really frustrating to try to identify which containers are vulnerable. In fact, work with your engineering team if you're in this particular situation to embrace ephemerality, even though ephemerality can be a bit frustrating as well. Ephemerality means that the instance isn't treated as an ongoing concern. It's temporary, right? And it's meant to be refreshed. And if you can automate that process, at refresh time, you're essentially introducing a container or a host operating system that is patched, configured to the latest requirements, and then you avoid that configuration drift as well. And then run immutable containers to avoid configuration drift. We talk about immutability, not changing a production workload in production. Make that change in the continuous integration, continuous delivery or deployment pipeline. Apply the patches, change any configuration that you have to, update any containers, and then redeploy them, and do that on a periodic basis. I think that the work is well worth the effort to ensure that environment is much easier to monitor and ultimately much easier to secure. So securing communications between components. My observation is that this is an area that isn't really typically enforced or it's not emphasized. So you have containers that can talk to any container in the environment, that can talk to any component in the environment. Usually it's unencrypted, right? There's no mutual authentication, right? So enforce mutual TLS, typically either through an orchestration solution or through what they call a service mesh, like a Istio. One of the byproducts of a service mesh that does control communication at the application layer is enforcing mutual TLS. TLS being the protocol that is used to encrypt HTTP or HTTPS traffic. Consider using certificates to enable mutual authentication as well. So not only encrypting that traffic but also ensuring that only machines that should be talking to each other are talking to each other. And then use network policies to control which components can communicate. Very similar to what you would do in a traditional network. Again, a service mesh can do that for you at the application layer, but doesn't really handle the network layer. So you do need some capability at the network layer, including things like IP tables to enforce those connectivity requirements and that segmentation. So treat containers as ephemeral, as I mentioned earlier. Refresh often and update the hosts and containers. And then check for sensitive directories mounted on the host, because any sensitive directories mounted on the host, especially if the container is running as root, are visible to the container. Then you have protecting secrets in transit and at rest, and this is one of the most significant challenges today. So don't hard code secrets in an image at any stage of the image creation process, because an image is created by layering files. And if you introduce and hard code a credential at any layer, you're not really removing that layer, right? And so you can actually decompress the image and actually see those credentials when it decompresses. So please avoid doing that. If you do find that, you have to really rebuild the image from scratch. Don't define secrets in environment variables either, because if a container is running as root, it has access to those environment variables. And then, of course, if the application crashes, typically those environment variables are displayed, right? And they're also captured in log files as well. Encrypt secrets in purpose-built secret vaults, like we talked about. HashiCorp Vault and other vaults are purpose-built to manage secrets and to encrypt them at rest and in transit. And then leverage features in orchestration platforms like Kubernetes and Docker Swarm to manage secrets as well, if that capability exists. And then consider encrypting, do encrypt secrets in transit, and don't pass secrets over the network unencrypted, and really avoid sending secrets to the network interface. That's just a bad practice. It's better to, the optimal approach rather is to pass secrets by writing them to a file accessed through a temporary directory held in memory. And the key word is temporary, right? It doesn't live persistently in memory. It basically instantiates in memory when it's required. And then, of course, it's ephemeral. And then avoid writing secrets to disk. Even in encrypted, because it's unencrypted when you're writing it to disk. And also you have to figure out a way to decrypt it, right? And so that introduces another challenge. All right, so that's all I have today. We are Align Technology Group. We are local. We are built and founded here. All of us are from Raleigh. We focus on securing, monitoring, technology platforms, whether they're in the cloud, whether or not. We're an AWS technology partner. And again, I appreciate your time. Thank you for coming. Yeah, questions? We have them. Yes, sir.
What do you think of the NSA recommendations for hardening Kubernetes?
I haven't reviewed them, but I think because they're the NSA, they're probably spot on. Yeah, I haven't reviewed them. And so there is a fundamental difference between the actual container and the container orchestration solution. I will take a look, though.
Mm-hmm. They updated pretty recently, actually.
Yeah.
Not my area of expertise.
Yeah. Yeah, I haven't reviewed them either. Anybody else? Yes, sir. I think the question is around performing forensics, both online and offline with containers. Is that fair? So a container is going to produce. Well, first let's face it. In a lot of environments, containers are ephemeral, right? here today, gone tomorrow. And so you may not have the container or even the host operating system to evaluate. If that is an important component, then as I mentioned earlier, you may want to host that particular workload in a lightweight, virtual machine, and maybe treat it as more persistent. Otherwise, you're going to be relying on the collection of all the system calls that the container made, when it was exploited, right? When privilege escalation occurred, and then of course when container escape occurred on the host itself. And so I would also evaluate the extent to which you're collecting the information you need on the host operating system, because the host operating system is the one that's, the kernel is the one that's evaluating those system calls as well. Does that make sense? Yes, sir?
Just a quick question. You mentioned updating patches. What patch repository would you look at out there and bring them in? There's a lot of patches, different environment sites to go to. I work at DoD.
Yeah. Obviously, it really depends on your needs, right? I mean, most third-party application patch repositories are a pay-for-play service. I can't recall any of them off the top of my head, even though I've used several of them. But what you would do is evaluate the kinds of third-party applications that you're running in your environment, and then determine the extent to which that third-party patch repository supports the applications, right? And then obviously the host operating systems that you're running as well. One thing I want to mention though is that it's a lot easier to patch in the application delivery process than it is to patch in production. It just introduces a lot of overhead and a lot of uncertainty too, right? Having been embedded with engineering teams, I've caused my share of problems when I patched. Even if I patched using the proper patch management process, going from test stage to prod, inevitably something happens in prod. So going off on a little tangent here, do consider patching in a non-prod environment, leveraging a source that satisfies all of the requirements that you're using in your environment. Where? Oh, it's like.
I was wondering if you could comment on a suggestion for secrets management, the secrets database that you maybe prefer or use, or what works best with containers?
It's not. There isn't one that I prefer. It obviously has a lot to do with the technology you're using, right? So a lot of orchestration solutions are introducing the capability to manage secrets. They may not be full featured though. HashiCorp Vault, seems to be a very popular one. If you're in AWS, then Secrets Manager or KMS rather, or Key Management Service is going to help. So my answer is it really depends on the platform and the solutions that you rely on to deploy, manage your containerized environment, or any technology for that matter that relies on secrets, right? But ultimately, you want to avoid, writing those secrets to environment variables. You want to avoid writing those secrets to disk. And you do want to leverage a purpose-built vault. And then you want to encrypt those secrets in transit, at rest, in between components that leverage those secrets.
Thank you.
You're welcome. Yeah, and I want to emphasize, none of this is easy, right? And I even underestimated the overhead associated with, securing a containerized environment. Once you start to really evaluate the permutations of what could possibly happen in this kind of environment, on the operating system itself, on the host, whether it's in the container, it gets really complicated. So it's a matter of really taking a risk-based approach, making some trade-offs. and then of course negotiating those trade-offs with the engineering team, but then emphasizing with the engineering team that the more efficient approach is really to automate as much of that in the application delivery process as opposed to production. I think they will be very amenable to doing that. Any other questions? Okay, just one last plug. For Liz Rice's book, Securing Containers, has been very influential, very informative. Really is the tip of the iceberg, though. And so I do encourage you to read that book if you're interested in container security. Read some of the Docker documentation, the Kubernetes documentation. It's still evolving, even though it's about 10-ish years old. And then a lot of solutions are out there that are coming along that are purpose-built to help you manage this environment, to monitor it, and ultimately secure it.
Thanks, Manny. For you?
Oh, thank you.
Thank you so much. Sorry, what did you say? Sorry, there's nothing in the
Oh, it's all.